Welcome back to the 8th chapter of the dark art of linear algebra, which opens with a discussion of orthogonal projections. Now, you have already met orthogonal projections in low-dimensional cases. For example, orthogonal projection onto a one-dimensional subspace, that is, onto a line through the origin, works as follows. We have some vector v, and to project it orthogonally onto this line simply means to drop a perpendicular from its tip to the line, and then the point where it lands, or equivalently the corresponding vector, is vector v's orthogonal projection onto the line. And if this line, the one-dimensional subspace, is called, say, W, we'll often denote the orthogonal projection as this string of symbols. Proj, for projection, obviously, of v, the vector that's being projected, onto W, written as a subscript. And often in this one-dimensional case, since a line is determined by any one vector lying upon it, we'll just put the name of a vector on the line as our subscript here. For example, let me erase those capital W's, and let's say we have a vector A that lies along the line. In that case, we might refer to V's orthogonal projection onto the line as the projection of V onto vector A, which we put as a subscript. It gives us the same information, since there's only one line that includes vector A, and A could be any vector on that line. It could even be pointing in the wrong direction, so to speak, so that it makes an obtuse angle with our vector V. It doesn't matter. It still picks out the same line. Anyway, this gives you an idea of how we denote an orthogonal projection onto a one-dimensional subspace and what it means geometrically. And of course, if we look at an orthogonal projection of a vector onto a two-dimensional subspace, which of course would be a plane through the origin, and let's go ahead and call that two-dimensional subspace W, then the idea remains much the same. If we take some vector V in the ambient space containing that subspace, we can project it down to the plane to obtain a new vector inside the plane, which is, of course, the projection of V onto W. Now, what makes this an orthogonal projection? Well, in the one-dimensional case, it was simply that when we drop the perpendicular, it makes a right angle with the line onto which we were projecting it. In this two-dimensional case, however, we're dropping the perpendicular not onto a line, but onto a plane. So we need that line, that perpendicular we dropped, to be perpendicular to the plane W. Well, what does that mean? Well, recall from basic geometry that a line is perpendicular to a plane if every line that lies in the plane and passes through the point where the perpendicular cuts the plane must be perpendicular to that line. So it's not just saying that two lines are perpendicular, it's making assertions about infinitely many pairs of lines. So that's what we would have here. Any line in the plane that passes through the foot of the perpendicular we dropped would have to make right angles with that dotted line. Not just one of them, but all of them. And the other thing I should mention while we have this picture up here, because it will be important for us later in the chapter, is that of all the vectors lying in plane W, all those infinitely many vectors, this one, the orthogonal projection of V onto W, is the one that is closest to vector V, which lies outside of the plane. Closest in terms of the distance between the points that those vectors correspond to. If we take any other point in the plane, its distance to the point corresponding to V is greater than the distance from V's projection to V itself. So an orthogonal projection gives us an important kind of minimum, which also means that, as you might guess, there is a calculus approach to this sort of thing. But we're not going to get into that since this is linear algebra. And anyway, the linear algebraic approach is much more elegant. But again, you get the idea. But you might not immediately get the idea if we jump up another dimension and consider orthogonal projection onto a three-dimensional subspace, much less onto a six-dimensional subspace, or a 912-dimensional subspace, or so on and so forth. It's not so immediately clear what these things even mean. When we're dealing with a one- or two-dimensional subspace, our geometric intuition guides us very nicely. But if, say, we're working in R42, and in that 42-dimensional space we have some 19-dimensional subspace, W, Well, that's a subspace, so it contains the origin, of course. And if we have some vector in our 42-dimensional space that does not lie in our 19-dimensional subspace W, and we call that vector V, what exactly does it mean to take our vector V, which lies in 42-dimensional space, and project it orthogonally onto this 19-dimensional subspace? I mean, yes, in analogy with the earlier cases, it should be the case that whatever point that gets projected onto, any lines in W passing through that point should meet the perpendicular we drop at right angles. But unlike these earlier cases with one-dimensional and two-dimensional subspaces, where we know what that looks like, and we can say, yes, obviously, there is such a projection lying in the one-dimensional subspace, and obviously there is such a projection lying in the two-dimensional subspace, I just can't call to mind a picture of a 19-dimensional space and say, oh yes, obviously, there is a way to do that. And if it turns out that there is a way to project a vector in a 42-dimensional space onto a 19-dimensional subspace orthogonally, it's not clear whether there's only one way to do that. I mean, it was perfectly clear in the lower dimensional cases that if I have, say, a two-dimensional subspace and a vector in the ambient space, that I can talk about the projection of the vector onto the subspace. The projection, singular. It's not like there's some other vector in the plane that is a different orthogonal projection of V onto W. No, there's obviously only one. But that's not so obvious in the high-dimensional cases, because we haven't spent our life moving around in 42-dimensional spaces. So we're going to need a little more than mere intuition to guide us in such cases. Now, it will turn out that there is a unique orthogonal projection of a vector onto any old subspace, no matter how many dimensions. But that's something we can establish with some linear algebra. And in fact, we're going to go further. By the end of this video, we will not only be sure that such a projection exists, we will be able to actually compute what the projection would look like, what the components of V's orthogonal projection onto W would have to be. And this is one of those times when skeptics in the audience might reasonably say, well, I can see how this is kind of interesting geometry, but it seems a little esoteric. I mean, I'm studying to be a computer scientist or engineer or economist or whatever. Questions about projecting 42-dimensional vectors onto 19-dimensional subspaces just seem pretty remote from my interests. I mean, it might be fun and artistic, but who would ever think of such a question anyway? Well, I hasten to reassure you that this is not an example of pure math for pure math's sake. Not that there's anything wrong with pure math, but the ideas we're discussing in this chapter turn out to be some of the most applied ideas in linear algebra, and by extension, in all of mathematics. We'll discuss this in full detail, not in the next video, but the one after that, but very briefly, just to show you why we might be interested in such a thing. Any field in which mathematics is applied is ultimately interested in approximations, and any situation in any field that can be modeled by a linear system, which we know comes down to something of the form AX equals B. Any system of linear equations can be written in that form. So more or less anywhere linear algebra can be applied. We know that systems of linear equations do not always have solutions. And yet, even if there is no solution to such a system, we are often interested in the nearest approximation we can get to a solution. And the way we think of that is to think in terms of linear transformations. We're looking for a solution X, which, as we said, in some situations will not exist. We could think of this as a vector or a point that the matrix A would transform into the vector B. Now, if no solution exists, that means that B does not lie in the image of matrix A. And of course, we know that A's image is a subspace of whatever ambient space we are working in. So if A is, say, a 42 by 42 matrix that captures whatever situation in whatever application of linear algebra, then we're working in R42. And A's image is some subspace of R42. And maybe that subspace is 19-dimensional. And like any subspace, it contains the origin, of course. And B, our target vector, well, that's some vector in the 42-dimensional ambient space. Now, we're looking for some vector X in R42 that gets transformed to our vector B. But there isn't one, because every vector in R42 gets mapped by A somewhere in A's image, which is only this 19-dimensional subspace, which doesn't contain vectors vector b. Oh, too bad, there's no solution to this thing. We have to go home. Well, not so fast. We may be interested in knowing, is there some vector that gets us as close as possible to b? Well, what does it mean to be as close as possible to b, and yet still to be in this image, in this subspace? That would be this guy, the orthogonal projection of b onto the image. So even though there is no x in R42 that gets mapped by a to vector b, there is some x in R42 that gets mapped to this vector, the projection of b onto the image. That's as close as we can get to a solution to this linear system. And that's often good enough. To mention very briefly an example that we will dwell on 2 videos from now, everyone has seen graphs like this, where we have a scatter plot of data. The data could be anything. It could be having to do with medicine, or economics, or politics, or sports, or anything, or physics. But we end up with some kind of scatter plot, and then through that plot, some mysterious line is threaded. And that is sometimes called the best fit line, which says something like, well, look, the data doesn't actually lie on a line. I mean, there's no line that passes through all of these points. That would be impossible. But if there was such a line, this is as close as we could get to one. So sometimes we can use this line to make predictions and so on and so forth about how one quantity depends on the other. Well, where does that line come from? As we will see, that line of best fit, best approximation, comes from precisely these kinds of ideas. And it's remarkable that something that can be shown on a page in 2 dimensions can be understood in a deep sense as connected to something having to do with the geometry of high-dimensional spaces. But all that's to come. I just wanted to give you a taste of the fact that this was not just daydreaming about what higher dimensional spaces might look like. Though again, nothing wrong with that either. That sort of thing is half the fun of mathematics. But that's where we are headed in this chapter. It will take a little work to build up to that point. And we are going to start at the bottom of the ladder and descend rung by rung, and we'll be at the top before you know it. So, starting from the bottom, we need to dwell on orthogonal projections onto a one-dimensional space. Or we might say orthogonal projection onto a line through the origin. But as I said at the beginning of this lecture, we often think of orthogonal projection onto a line as orthogonal projection onto a vector that lies on that line. Because every vector, of course, well, every non-zero vector, determines a line. But I'm going to go one step further. Rather than working with any old vector that lies on the line, let's restrict our attention to a unit vector. We often use unit vectors to indicate direction because their magnitude doesn't vary. So all they're good for is pointing out a particular direction. Anyway, let's call our unit vector u, or u hat. I put the little hat over it to indicate that it's a unit vector. So let's talk about orthogonal projection onto one-dimensional subspaces, or equivalently, onto a unit vector that lies along such a subspace. If we project our given vector v orthogonally down onto the line on which the unit vector lies, then our projection vector, which I've translated away from the line to avoid traffic jams, is what we are interested in here. What can we say about it algebraically for now? Well, certainly it is a scalar multiple of u, the unit vector. So I'll just say that the projection vector is some mystery scalar times u. Our first task will be to figure out what this scalar must be, in terms, of course, of v and u. Well, this is actually very easy if you have a good geometric understanding of the dot product, which is all about scalar projections of vectors onto other vectors. And in particular, if we have 2 vectors, a and b, and their included angle is called theta, then their dot product is the length of a, which we could think of as a's scalar projection onto itself, times the product of b's length and the cosine of that angle theta. And by very basic trigonometry, good old SOHCAHTOA, everybody knows that that product is the scalar projection of b onto vector a. So the length of the side of this little right triangle. So at the end of the day, a dot product is just a product of these 2 lengths, those 2 scalar projections. Well, the scalar we are after in our picture is one of those 2 scalar projections. So we might think, well, what is the dot product of v and u? That's the product of those 2 scalar projections. V's scalar projection onto u and u's scalar projection onto u. But u's scalar projection onto u is just u's length, which is 1 because it's a unit vector. So that means the dot product of v and u is the product of the thing we want, and 1. So the dot product is just the thing we want. It is the scalar that we scale u by to bring it up to the vector we want. So that scalar is nothing but v dot u. And we have it. A very important little formula. Let's write it up so it's not on an angle. The orthogonal projection of a vector v onto a unit vector u, very important that it is a unit vector, is of course some scalar multiple of the vector u, and in particular it is v dot u times u. Again, u stands for unit vector. If it isn't a unit vector, this formula doesn't work. It's easy to come up with a formula for cases where it's not a unit vector. It's just a little more complicated. You'll figure that formula out as one of your homework problems in the book. And before we start stepping up the ladder to higher dimensions, let's just do a very quick numerical example. Let's work in R4 to show that this still holds where we can't see it. And you might say, wait a second, I thought we derived all of this just in the case of R2. Well, no, not necessarily. Remember, we did everything without coordinates. We were working coordinate free. These two vectors, v and u, might be vectors in, say, R10,000, but we don't care about the ambient space. Even if they are vectors in R10,000, u still generates a line in that ambient space of however many dimensions, and u and v together determine a plane in that gigantic space. All our work was just in that gigantic plane. We didn't care whether the ambient space was simply 2 dimensions and nothing more, or 3 million dimensions. So this holds in any number of dimensions, but it still only refers to projections onto a 1-dimensional space, a line. Anyway, so let's work in R4. In R4, let's let vector v be 10, 2, 8, 4. Those are its standard coordinates. And let's consider a unit vector whose coordinates are half, half, minus half, half. You can check very quickly that that is indeed a unit vector. The squares of each component are 1/4. Add those all up, you get 1. Take the square root, you still get 1. So this, yes, is a unit vector in R4. Anyway, given this vector and that unit vector, let's find the orthogonal projection of v onto the unit vector. Well, according to the little formula we just derived, that's going to be v dot u times u. Obviously, it's going to be a scalar multiple of u, and the scalar is just v dotted with u. Well, when we dot v and u, we get, let's see, 5 plus 1 is 6, minus 4 is 2, plus 2 is 6. So we end up with 6u, or if you want to write that out, since we have u's components here, that would be the vector whose components are 3, 3, minus 3, and 3. And we've got it. As easy as it could possibly be. So great little formula. Next, I want to start thinking about the 2-dimensional case, when we are projecting a vector v in whatever ambient space onto a 2-dimensional subspace W. And we're interested in this 2-dimensional case mainly because it will help give us the insights we need to think about orthogonal projections onto subspaces of any number of dimensions. The key idea, as we discussed earlier in the video, is that V's orthogonal projection onto plane W, which I'm just going to call vector P for short, has a very particular relationship with V. Namely, if we look at this vector, which is the vector we must add to P to get V, and therefore algebraically it must be vector v minus p. P plus v minus p is obviously v. That vector, which goes from the tip of p to the tip of v, is going to be perpendicular to every vector in the plane. I've translated typical vectors to this point so that we can see the perpendicularity. It is that property that ensures that vector p, v's projection onto the plane, is the vector in the plane that is closest to our original vector v. After all, suppose that we had, in a less messy figure, the same setup and someone were to come along and claim, no, you've got it all wrong. Vector p isn't the one that's closest to v. There's some other point in the plane W, this one, and it's actually closer to the tip of V than P's tip is to V's tip. So there, you're wrong. Well, we could very quickly demonstrate that this person was out of his mind, or at least wasn't thinking straight, because if this property holds with all those vectors in the plane being perpendicular to V minus P, well, think about how that would play out here. I will just draw in a few lines creating this little triangle, and we will see that the person making that claim must have been wrong. Think about the angles in this triangle. We know by this property over here that we have a right angle right here. So it is a right triangle. Now think about the two distances that we were comparing. The distance from this new point that our interlocutor proposed, and v's tip is the length of the hypotenuse of that right triangle. And of course, the hypotenuse is the longest side in any right triangle. So that means that distance is greater than the distance from p's tip to v's tip. So that person is wrong. This point, or equivalently, that vector, is not closer to v than p is. And no matter where you put that point in the plane, the exact same argument would hold. Its distance to v's tip will always be greater than the distance between p's tip and v's tip. So this property of perpendicularity truly does ensure that among all the vectors in W, p is the closest to v. So that perpendicularity property is what we want to hold, even in cases where we're not projecting down onto a plane, but we're projecting down onto a 97-dimensional subspace, or whatever it may be. In that case, we'll want some vector p, which has the property that v minus p will be perpendicular to all the vectors in the subspace of however many dimensions. And of course, we express the notion of perpendicularity when we're dealing with vectors in the language of dot products. So the question is, if W is some subspace, let's say a k-dimensional subspace of some larger vector space, and we have some vector v from that ambient vector space, is there some unique vector p in the subspace W, like so, such that this vector joining the tips of p and v, namely v minus p, gives us a dot product of 0 when we dot it with vector w, where vector w can represent any vector in the subspace, capital W. So is there such a vector p such that the vector from its tip to the given vector v's tip has a dot product of 0 with every vector in the subspace W? If such a vector p exists, we will define it to be vector v's orthogonal projection onto the k-dimensional subspace W. Hopefully, with all our preliminary work, that question seems well motivated and makes sense to you. Because if there is such a vector, then that condition would still guarantee, even if the subspace is 10,000 dimensional, that p is the closest point in subspace W to our given point V. The extra dimensions don't change anything, because if W is a 347-dimensional subspace, and we have our vector V and some vector P inside of the subspace that satisfies this condition, then no matter what other point in W that somebody puts forth claiming that it's closer to V than P is, we will know it's nonsense. Because if we look at V minus P and consider the vector from its tail to the proposed alternative point, we know by this condition that since this green vector lies in W, its dot product with V minus P is 0. In other words, it is perpendicular to it. So if I now draw this last side of this little right triangle, we can see that even though we're working in a 347-dimensional space, actually in a larger ambient space than that, this little triangle still exists on some ordinary two-dimensional plane within that larger space. And so it still obeys the basic rule that the hypotenuse of any right triangle is obviously the longest side of that triangle. So that means that the distance from that proposed alternate point to V's tip is not shorter. It's longer than the distance from P's tip to V's tip. So if we have a vector P that satisfies this condition, it is definitely the one that is closest to V, no matter how many dimensions we are working in. And therefore, it is an eminently sensible condition for us to use to define the notion of a projection. Okay, good. We're satisfied that we have the condition we want. But the question remains, is there actually such a vector? Well, let's begin working our way towards an answer. What we're going to do is to figure out algebraically what such a vector P would have to look like. Well, let's see. The simplest fact about P is that, of course, it is going to live in the subspace W. So that means if we have some basis of W, which would consist of k basis vectors, since it's a k-dimensional subspace, if we have such a basis, our vector P would have to be a linear combination of those basis vectors. So let's go ahead and give names to the vectors in some basis for W. In fact, since we are interested in a question that involves dot products, let's consider not just any old basis for our subspace W. Let's let U1, U2, all the way up to UK be an orthonormal basis for W. In other words, a basis where the basis vectors are mutually perpendicular, like the standard basis. And not only mutually perpendicular, but unit length as well. That's the normal part of orthonormal. Orthonormal bases are especially nice to work with when we're thinking about dot products, because as we discussed back in chapter 6, the familiar formula for a dot product, where we multiply corresponding components and then add up the results, still works if our coordinates are given according to an orthonormal basis. Moreover, since our basis vectors are mutually orthogonal, and we're thinking about dot products, that means if I pick any two of the basis vectors and take their dot product, that would be 0. And since they're orthonormal, since they are unit length, if I take any one of the basis vectors and dot it with itself, I get the square of its length, so that would be 1. So those are nice properties, and in fact, you will see them show up very soon. Anyway, this kind of thing explains why I would like to use an orthonormal basis as opposed to any old basis. So we take any such orthonormal basis, U1, U2 down to UK, then we know that our vector P, being an element of this k-dimensional subspace, W, will be some linear combination of them. C1U1 plus C2U2 all the way down to CKUK, where those C's are some unknown scalars. Well, our task is going to be to figure out precisely what those unknown scalars must be in order to make P have this required property. The hope is that maybe we can figure out what the scalars are in terms of the given vector V and the vectors in the orthonormal basis. If we could do that, then we would know how to project a vector orthogonally onto any subspace, provided we could find an orthonormal basis for that subspace. So let's see what we can figure out about those constants, C1 through CK. Well, we don't have that much to work with. What do we know here? We know that P, our prospective orthogonal projection, has this special property that if you subtract it from the given vector V and then take the dot product of that difference with any vector at all in the subspace W, we'll get 0. That's a powerful condition, so maybe we can squeeze something out of that. So if P satisfies, what should I call this condition? I will call it the orange star condition. So if P satisfies condition orange star, then in particular, we'd know that a lot of dot products are equal to 0. And one way we could get 0 is to take the dot product of V minus P and, well, what's a specific vector that we know is in W? Well, we know all the basis vectors are in W, so let's use the first basis vector, U1. So if P satisfies this condition, we know that we would get 0 if we dot V minus P with U1, the first basis vector. Well, okay, that's true, but does it tell us anything? Well, let's do a little algebra. We proved back in chapter 1 that the dot product distributes over vector addition, or subtraction, which is just adding a negative. So that means I could rewrite this stuff as V dot U1 minus P dot U1. All right, fair enough, but does that help us? Well, it might, because look, we actually have this alternate expression for P, where we wrote it in terms of the basis vectors. Hey, I think I can see what's happening here. So let's expand that P out as that linear combination and dot it with U1. That's nice, because then I can distribute that dot through that giant vector addition. Oh, and this is exactly what we were talking about before, why an orthonormal basis might be useful here, because we're going to end up dotting U1 with all of those individual basis vectors, like so. And remember, the reason why we said that would be nice is that expressions like this, U2 dot U1, what's that? Well, it's an orthonormal basis. So these vectors are all mutually orthogonal. So U2 dot U1 is going to be a big fat 0. And the same thing with U3 dot U1, which would be in the next term, another 0. And U4 dot U1, another 0. All the way down, all those things would be zeros. So I'll cross them all out, except this first term, where I have U1 dot U1. Well, you dot a unit vector with itself, and you get 1. So this term just becomes C1. And this whole expression collapses into V dotted with U1 minus C1. And this expression is equal all the way back 0. But if this stuff is equal to 0, we'll add C1 to both sides, and we conclude that C1 is equal to V dot U1. Hey, that's terrific. That is just the sort of thing we were looking for. We wanted to get those scalars, those coefficients, in terms of the original vector V and those orthonormal basis vectors. And that's exactly what we have. The first one of those scalars is just v dotted with the first orthonormal basis vector. And we got that by letting this w in our orange star condition be u1. Well, guess what would happen if we let it be u2? I'll show you after moving our conclusion over here so we don't forget it. If instead of u1, we made that u2, well, we could still distribute that through. The only changes would be we would have to change those subscripts to 2. We could still expand p out in terms of the basis vectors. Again, I just need to change those 2 subscripts to 2's. And then on the next line, what's going to happen after we distribute that dot product of u2 through? Same kind of thing last time, except a different term will be the one that survives. This first term involves u1 dot u2. Well, we know that's 0 by the orthogonality of the basis vectors. The second term involves u2 dot u2. Well, that is 1. So that term just becomes c2. The next term would involve u3 dot u2. So it would be 0. And all the way down, all the other ones would be 0, including the last one, which has uk dot u2. All that survives from that big expansion is just the c2. So that all this stuff just collapses to v dot u2 minus c2. That's equal to 0, so adding c2 to both sides allows us to conclude that c2 is v dot u2, which I'll write up here. So now we know not only what the first constant is, but also what the second constant is. And I'm sure you can see the same thing happens all the way down until we get to the kth and last constant, which will be v dotted with uk, the last of the orthonormal basis vectors. So now we know what all of the constants we were looking for look like in terms of v and the orthonormal basis vectors. So let's do some compression over here as we continue our work towards an answer. For some vector p to satisfy the condition we want, then in particular, we can deduce, as we just did, that ci is v dotted with ui for all the I as I runs from 1 to k. Hence, we know something about p. We know that it is equal not just to this very general expression, but if we substitute in for all of the values of c, we get this expression. P is not merely c1 u1, but v dot u1 u1. And then we add not just c2 u2 for some unknown c, but v dot u2 u2, and all the way down to v dot uk times uk. This vector satisfies this condition that if you subtract it from v and dot it with w, you get 0. We have seen for all these basis vectors. And so by linearity, since it holds for everything in the basis, it holds for everything in the space altogether. That's the whole reason we like a basis in linear algebra. If you understand what happens to the basis, you understand what happens to everything in a space. So this vector is, in fact, the projection of v onto an arbitrary subspace W. So as long as we can find an orthonormal basis for W, not only do we know that such a vector exists and is unique, but we know exactly how to compute it. And before I summarize all this, let's just observe how this connects with something we discussed earlier. Look at all these individual terms. What are they? Well, they should remind you of something we discussed earlier. Each term is a projection of the vector v onto an individual basis vector. This first term, for example, is the projection of v onto u1. That's what this recipe tells us. And the second term is the projection of v onto the second basis vector, and so on and so forth, all the way to the end. So what we have is that p, our projection of vector v onto the subspace W, that projection is a sum of all the individual projections of v onto each individual basis vector in an orthonormal basis for W. So again, all praise to orthonormal bases. And in the next video and section in the book, we'll talk about how to turn any given basis into an orthonormal basis. But this gives you a sense of why we like to do such a thing. But I think that's pretty neat, that if you have an orthonormal basis, you can project a vector onto a 300-dimensional subspace simply by projecting onto 300 individual one-dimensional subspaces and adding up the results. So let's summarize all this mess. If we want to project a vector v onto a subspace W, we can find an orthonormal basis, u1 through uk, for that subspace, then compute that the projection of V onto the subspace W is the sum of the projections of V onto each individual orthonormal basis vector. So U sub I, as I runs from 1 to k. And since we know how to do those individual projections onto vectors, that is, onto one-dimensional subspaces, which we learned earlier, we could rewrite that as the sum of V dot UI, that scalar, times UI, as I runs from 1 to k, going through all the orthonormal basis vectors. And we've got it. We have answered our original question. Let's do a quick numerical example. Let's let W be a subspace of R2. More specifically, the plane whose equation is x minus y minus 2z is 0. That, of course, is a plane through the origin. Given the following orthonormal basis for W, these two vectors, u1 and u2, find the orthogonal projection of vector v, which we'll take to be 1, 2, 3, onto this subspace W. Now, I have a few comments before we begin in on the actual solution. First, you should take a moment and confirm that these two basis vectors, u1 and u2, are actually an orthonormal basis for W. That means checking a few things. First of all, do these vectors actually lie in the plane? They do, and that's just a matter of confirming that their coordinates satisfy the plane's equation. Okay, so they lie in the plane. Do they constitute a basis for the plane? Well, that's easy to see, because any two linearly independent vectors in that plane constitute a basis for it, and looking at their coordinates makes it obvious that these vectors are linearly independent. They are not scalar multiples of one another. Okay, so they are a basis for W. Is it an orthonormal basis? Well, that requires checking two things. Are these two vectors orthogonal to one another? That's easy to confirm just by taking their dot product and showing that it's 0. And then also, are they unit vectors? Are their lengths 1? That too is easy to check. So I'll leave those details for you, but it's worth asking yourself, where did this orthonormal basis come from in the first place? It's not hard to find a basis for W. Just find two linearly independent vectors in W, and it's easy by experimenting to find them just by finding values of x, y, and z that satisfy the plane's equation. So it's easy to find a basis. And of course, it's easy to normalize the basis vectors. But how do I get a orthonormal basis? How do I get it so that they are perpendicular to one another? You might want to take a few minutes and just try to think about that, because if you've considered that problem, how to find an orthonormal basis for a subspace, then you will appreciate the solution that I present in the next video involving the so-called Gram-Schmidt orthonormalization process that much more. But that's to come. For now, we're just assuming you've been handed an orthonormal basis. And indeed, you have been handed one. So let's find the orthogonal projection of this vector, 1, 2, 3, which, who knows, maybe looks something like that, onto the plane. How are we going to do it? Well, we just follow our summary of results here. We have an orthonormal basis, so we know that the projection of V onto W, this two-dimensional subspace, is nothing more than the sum of the projections of V onto each basis vector. So we reduce it down to projections onto one-dimensional subspaces. And everybody knows how to do those. That's the formula that everyone remembers because it's so simple. So we'll get V dot U1 times U1 plus V dot U2 times U2. Fill in those details, do some boring arithmetic, and you will soon arrive at the answer. 1/6 of the vector 13, 5, 4. So that gives us the coordinates of the vector we seek, the orthogonal projection of V down onto subspace W. Nothing to it, except, of course, that niggling problem of how do we come up with an orthonormal basis if we are not handed one. But as I've said many times now, we will address that in the next video. All right, should I end this one here? Make it a nice short one? Well, this is where I end the section in the book, so if you want to stop it here and just jump into the exercises, you could do that. But I want to show you something else related to projections that's pretty interesting. I don't do this in the book because, strictly speaking, it's not necessary, but it is interesting. So I want to show you a related but different approach to projection. I'm going to use what we've discovered already to show you how to write down the standard matrix for projection. Because after all, orthogonal projection is a linear map, so I should be able to represent it as a matrix. And at first you might think, well, that's not such a big deal. You use this formula to figure out what the projection does rows to all the standard basis vectors, and those become the columns. That's true, and if we were just interested in one concrete case, such as the one we were describing here, that'll work just fine. But if we want to come up with a general recipe for how to do it in any case, that approach is awkward, as you'll see if you try it for yourself. So here is the problem. If W is a k-dimensional subspace with an orthonormal basis, that's what my ON stands for, with orthonormal basis U1, U2, all the way down to UK of Rn, so it's a k-dimensional subspace in an n-dimensional ambient space, then orthogonal projection onto W is a linear map from Rn to Rn. Depicted schematically, here's Rn, here's a subspace W, here are a few vectors in Rn. We can transform Rn by projecting everything down, or up as the case may be, onto the subspace. Incidentally, the rank of that linear map, to review some old vocabulary, would be K, because of course the image would simply be W, and it is a k-dimensional subspace. That also means, to continue the review, that the nullity of that map, the dimension of the kernel, would be n minus k, because by the rank nullity theorem, those things have to add up to n. That's neither here nor there. It's just the teacher in me feels compelled to throw in a little review where I can. But anyway, we've got this linear map on Rn. It's orthogonal projection. That map, of course, can be represented by a matrix, and our problem is to find the standard matrix representation of this orthogonal projection. It's a map from Rn to Rn, so this is going to be an n by n matrix. And our solution to this problem is going to involve some wickedly clever algebra. Strap in. We begin with what we know already. The projection of V onto this k-dimensional subspace W is the sum of its projections onto each of the one-dimensional subspaces spanned by the vectors in the orthonormal basis. And we know how to compute projections onto one-dimensional subspaces. That's a piece of cake when the one-dimensional subspace is described by a unit vector. So each one of these terms can be replaced by something of this form, a scaled version of U sub I, where the scalar is just V dotted with that U sub I. We know that, everybody knows that. So far, so familiar. Now is where we will start getting clever. Forget about the sum here. Just think about each individual term. In each term, we have something of the form V dot Ui times Ui. That's a scalar times a vector. Forget about the specifics. Just think of it as a scalar C times a vector A. Scalar multiplication, the product of a scalar and a vector. We introduced this literally on day one. A very old friend. We were talking about multiplying a scalar and a vector long before we ever encountered the idea of a matrix, which didn't occur until chapter 3 of the book. But you know, we've traveled a long road since then, and sometimes we can look back with the knowledge we have now and think about familiar things in new ways. So rather than thinking of these as two fundamentally different objects, a scalar and a vector, I can actually think of this, if I squint my eyes a bit and rewrite it in a slightly different form, as a kind of matrix multiplication. Start with a vector itself. We're talking about, in the place this is coming from, a vector with a certain number of components in standard Rn coordinates. In particular, it would have n components. But I could think of a vector with n components as an n by 1 matrix. All right, well, that's not too strange. But what about the scalar? That's just literally a number. Well, does that mean I can think of a scalar as a 1 by 1 matrix? I sure can, although there is one little problem here. I can't multiply a 1 by 1 matrix and an n by 1 matrix in this order, because those inner dimensions don't match. But if I reverse the order, now I've got n by 1 times 1 by 1, the inner dimensions match, and that means their product, as a product of matrices, is indeed an n by 1 matrix, better known as a vector with n components, a column vector, which is exactly what this should be. So this should work. Just to convince ourselves, let's do a quick numerical example. Suppose we take the vector 1, 2, 3 and scale it by 4. Well, of course, we get 4, 8, 12. But what if I thought about it this way? Then I would want to rewrite that as 1, 2, 3, the column vector, or 3 by 1 matrix, times the 1 by 1 matrix 4. And let's make sure if we multiply that out, everything works out as it should. We've got 3 by 1 and 1 by 1, so this should be a 3 by 1 matrix, a column vector. And if we do the matrix multiplication, which sounds funny, but we can still carry it out using, say, the entry perspective, the entry in row 1, column 1 in the product is the dot product of row 1, which consists of just one number, and column 1 in the right matrix, which again just consists of one number. So that's 1 times 4, which is 4. The entry in row 2, column 1 of the product is the dot product of row 2 of the left matrix and column 1 of the right matrix. So that, of course, is going to be 8, and the last one will be 12. And yes, this does match up with what we get doing scalar multiplication in the normal way. Anyway, this might seem like a bizarre way to do scalar multiplication, but the fact that we can think of it as matrix multiplication, if we put the scalar on the right, can sometimes prove helpful, and it will prove helpful up here. So instead of having for each term this scalar, that dot product, times this column vector, I'm going to rewrite that by putting the column vector first and the scalar, which I'm actually thinking of as a 1 by 1 matrix, second. Okay, fine. So I'm thinking of this now as matrix multiplication, each term, where this, I guess I should have also written, is an n by 1 matrix. And now I'm going to do something else, which might look pointless, which is that I'm going to simply reverse the order of the two vectors in that dot product. I mean, we know we can do that because the dot product is commutative. We proved that way back in chapter 1. But why on earth would I do that? Only to set this up for yet another move, which is going to be to trade my dot product so that it goes away and I end up with more matrix multiplication. So I'm going to take this and rewrite it in a way which I think we have used once before. Any dot product could be rewritten by a trick using the transpose. Take the first vector and take its transpose and then just multiply by the second vector, right? I mean, again, for a quick numerical example, if I have the dot product of 1, 2, 3, and 4, 5, 6, okay, that's 32, but I could have written that as this stuff, right? 1, 2, 3 as a row vector. In other words, a 1 by 3 matrix. And we keep 4, 5, 6 as a column vector. In other words, a 3 by 1 matrix. So their product is defined because the inner dimensions match, and we end up with a 1 by 1 matrix, which of course, as we've said before, is a scalar, and that would be 32. Or if you want to be very fussy, the matrix whose one entry is 32, but we're not going to be that fussy. Anyway, that's all we're doing here. And now each term is actually a product of 3 matrices. We've got UI, which is a column vector or an n by 1 vector, UI transpose, a row vector, that's a 1 by n, and V, which is another column vector, n by 1. Now, thinking of this as a product of 3 matrices, we might remember from all the way back in chapter 3 when we first learned about matrices that matrix multiplication is associative. In other words, if I have a product of 3 matrices, it doesn't matter whether I have the parentheses there and I write ABC as A times the quantity BC, or if I put the parentheses here so that I have the product AB times C. The associativity of matrix multiplication was something we get for free once we recognize that matrix multiplication corresponds to composition of linear maps. In other words, composition of a special kind of function, because function composition is always associative. So anyway, since I'm thinking of these as 3 matrices, I can reassociate. I can do some regrouping and write each term like this. So now I've got a sum of terms where each term is UI times UI's transpose times V. But wait a second. Think about that stuff in parentheses. UI times UI transpose. UI is an n by 1 matrix, a column vector. UI transpose, of course, is a 1 by n matrix, a row vector. They are compatible because the inner dimensions match, and their product is an n by n matrix. So I'll write that up here. So now think about this sum. We've got k terms. Each term is a different n by n matrix for different values of I, as I runs from 1 to k, times V, right? Expanded out, that would look like this, where the white stuff in each term is a matrix. These are all different matrices. Well, I can factor this V out of all of them and rewrite that stuff as this, where I've got a sum of matrices, and that sum, which itself is a matrix, gets multiplied on the right by that vector. So in other words, I'm summing first and then multiplying, whereas over here, I'm multiplying and then summing. So I could rewrite all that stuff like this, where I've simply factored the V out of every one of the k terms on the left. Good. Well, this is all very strange looking, but let's take a moment and see where we are. Each one of these terms in the previous step we said was an n by n matrix, and then we added them all up. Well, the sum of n by n matrices is of course still an n by n matrix. So what we have shown here is that to get the projection of V onto subspace W, we can take this crazy looking thing, which is in fact an n by n matrix, and multiply it on the right by V. That matrix is what turns V into its projection. So this is the matrix we want. And you might say, well, that's all very interesting, but that really looks like a pain to compute. I mean, after all, it involves adding up k different n by n matrices. Well, here's the last bit of devilishly clever algebra. This stuff in parentheses turns out to be AA transpose, where this mysterious matrix A is the matrix whose columns are the vectors in the orthonormal basis for our subspace. Oh, well, that's not so bad in that case, because then once we have our orthonormal basis for our subspace W, it's easy enough to write down a matrix whose columns are its vectors, transpose it, and multiply it, and that will be our projection matrix. That product, AA transpose, will be the standard matrix representation of the orthogonal projection we are looking for. Phew! I need to say a few things. First, it is not obvious that this last equal sign I wrote down is justified. Why is it that this crazy sum of n by n matrices is equal to this product, AA transpose? It's actually not hard to prove that, and if I'm feeling particularly vigorous, maybe I will write down the sketch of a proof and superimpose it on this video when I edit it. I guess you know if you're seeing it right now. But whether I do or not, it's not a very satisfying proof, because it's the kind of thing that if somebody says, prove that this is equal to that, well, okay, you can do it. But how would you have thought to have recognized that this was really just that if it wasn't handed to you on a silver platter? Not at all obvious. Okay, so that's one thing I wanted to say. What was the other one? Oh yeah, I guess we should summarize this and then do a quick numerical example. Maybe I'll redo the example we did before. But still, before I do that, even if this last equal sign is a little dicey to you, I hope you appreciate the weird algebraic trickery we did in there. I told you it was clever. All right, back to the summary. If W is a k-dimensional subspace of Rn with orthonormal basis u1, u2 down to uk, then the standard matrix representation of orthogonal projection onto W is AA transpose, where A is the matrix whose columns are the vectors in that orthonormal basis. Notice, by the way, that this is not in general a square matrix, because each column has n components because it's a vector in Rn, but there are only k of them. So this is an n by k matrix. That's A. A transpose would therefore be a k by n matrix, and when you multiply the two together, you get an n by n matrix as expected. All right, to finish this off, as an example, we will revisit the same problem we had earlier in the video. Here are our two vectors, u1 and u2. They constitute an orthonormal basis for W, which is a subspace of R3, a two-dimensional subspace, obviously, since there are two basis vectors. We want to find the standard matrix representation for orthogonal projection onto W, and once we have it, we will use it to find the projection of vector V onto that two-dimensional subspace, where V is the vector 1, 2, 3. That's the one we did in our previous example. We want to show that we still, of course, get the same answer. So the projection matrix is, I'll call it P for projection, the product of a certain matrix and its transpose. So this is our matrix A. Its columns are the vectors in the orthonormal basis, but that's not P. I still need to multiply by the transpose of that matrix. This matrix was a 3 by 2 matrix, so its transpose will be 2 by 3. There's the transpose, and if you multiply those two guys together, you will get this stuff. A 3 by 3 matrix, which you will note is also a symmetric matrix. Symmetric matrices have nice properties, but I don't want to get distracted in this long video. Anyway, we have our projection matrix. This is nice because we could use it to now project any vector in Rn onto our two-dimensional subspace W. For example, the projected image of the vector 1, 2, 3 is that symmetric matrix times the vector 1, 2, 3, which, if you work it out, turns out to be 1/6 of 13, 5, 4, which should ring a bell because we saw it when we found it by other methods earlier in the video. Okay, so now you know two ways to carry out orthogonal projections onto arbitrary subspaces, either as a simple sum of projections onto one-dimensional subspaces, or this other method where you come up with an actual projection matrix. And now, go forth and project. Goodbye.